Hi guys, I hope you're having a fabulous day. So what I'm going to talk you through real quick is worksheet 5, Harmonious Frequencies. And I'm going to talk you through part 1 and then you can complete part 2 and part 3 on your own. Okay, so part 1 says it's a string that's fixed at both ends. And we're talking about a standing wave pattern being created on this string that's fixed at two ends. Okay, so both ends, we know if there's a pulse traveling, the pulse is going to reflect on the opposite ends, and the pulses, as they interfere, are creating resonance, and so that's going to increase the amplitude, and we're going to have a standing wave develop. So the first question on part 1 says, in order for a string that's fixed on each end to resonate, one end must be blank, a node or antinode. The other end must be blank, a node or antinode. Because those are fixed, so because those are sitting there right, like stuck in that position, those both have to be nodes. Okay, a node is the place where it's not going to have any amplitude, and if that can't wiggle at all, either side, those are going to become nodes. So it should be node and node. And then it says, for the following examples, assume that the speed of the wave is 600 meters per second and that the length is 1.2 meters. So what we want to do is sketch the first harmonic. Harmonic is a way of describing a standing wave pattern. And the easiest way to remember it is it's the number of antinodes you're going to have. So the first harmonic has one antinode. So we've got our two nodes on the end, one antinode in the middle, and so it's going to look something, I don't know why these dots are here. I'm on the wrong side, that's why. That's okay, we'll go back. Looks something like that one. Awesome. Okay, so that is what the first harmonic on a string that is fixed at both ends, that's what the first harmonic would look like. You can see it's got one antinode, and I count this as one antinode. Obviously there's an antinode here, an antinode here, but this is one total antinode instead of like multiple right next to each other. So how many wavelengths are represented here is the first question. How many wavelengths? So take a second to think about that. This is actually half of a wavelength, okay? So a wavelength would be a sine curve. It would be up and down. This is just half of that. So this represents half of a wavelength. So what is the total wavelength of this wave that's making this standing wave pattern? It would be 2.4 meters, right? If we were to look at one full wave, we'd have to include the second half of it, and since this half wavelength is 1.2 meters, the full wavelength is going to be 2.4. So then part C says, what's the wavelength in terms of L? And so that would just be, if this is L, right here on here, what is the wavelength in terms of L? And since L is half of a wavelength, then full wavelength would be 2L. And so then we have to go in and solve for the frequency. So we know the wavelength is 2.4 meters. We know the velocity up top on the sheet is 600 meters per second. So you have 600 equals frequency times 2.4 meters. So V equals F lambda, our equation from the lab yesterday. That equation. And you get 250 hertz. So you do 600 divided by 2.4. So you get 250 hertz for the frequency of this wave. And then E says, what's the frequency in terms of V and L? And so it would be V divided by half, or 2L. Oops, and you can't see that because the 2.4 is twice of this length. All right, so let's take a look at the second one. So this one says, sketch the second harmonic. So you've got still your two fixed ends. The second harmonic needs two antinodes. So it's going to look something, we're going to have another node in the middle. And so you'd have an antinode, and like that. So this is your second harmonic of a standing wave pattern. Again, this length of the string is still 1.2 meters. And so the question is, how many wavelengths are represented here? And here we've got a full sine wave. We've got up, down, back to 0. So this represents one full wavelength. So one full wavelength is visible. And so what is the wavelength? It's 1.2 meters. We know if this is one wavelength and the length of the string is 1.2, the wavelength is 1.2. What's the wavelength in terms of L? It would just be L because this is the length of the string represents one wavelength again. Calculating frequency, same way we did that before, V equals F lambda. So V is the 600, frequency is what we're looking for, lambda is 1.2. And you get 500 hertz for that. So 600 divided by 1.2, 500 hertz. What's the frequency in terms of V and L? So we would do V, which is that, divided by L. So it would just be V over L. And now they're asking for frequency, F2, in terms of the first harmonic. And so that's going to be useful to look at the equations you wrote for E. So up top, we wrote it was V2L, and this one's VL. Oops. So see if you can figure out what F2 is going to be equal to in terms of F1. So is it going to be half F1, 2 F1? Think about that for a second. You should get 2 F1, right? Because it's the first frequency was 250 hertz, this one's 500 hertz. And you can look at the equation for that as well. All right, so third harmonic now. So if there's third harmonic, in the second harmonic we had 2 antinodes. So now we're going to need 3 antinodes, which means if I've got 2 fixed ends, I'm going to have 4 nodes. So you want to add in 2 nodes there. And then we're going to draw our wave. So it would look something like this. So you can see this has 3 antinodes, 1, 2, 3, and that's why we call it the third harmonic. So how many wavelengths are represented here? We have a full sine curve plus another half of a sine curve. So this is 1.5 wavelengths. So what is 1 wavelength? What's the length of 1 wavelength? Well, if 1.5 is 1.2 meters, you need to do some algebra to figure out how much of that is just this one. So I would take 1.2, a couple ways to do it. You can say 1.2 equals 1.5 times the wavelength and solve for a wavelength. Or I think of, okay, this is like 3 chunks. And so if I take 1.2 divided by 3 chunks, I get 0.4 for each chunk. And a wavelength is going to be 2 of those, so it's going to be 0.8. So lambda is 0.8 because that's the distance for just this part right here. So in terms of L, lambda would be 2/3 of L, right? So 2/3 of this length of the string is 1 wavelength. Frequency, V equals F lambda, so we plug in 600 for the V. Lambda is 0.8, so 600 divided by 0.8, 750 hertz. Frequency in terms of V and L, so it's going to be V, that didn't change, divided by 2/3 L for the wavelength. So you get 3V over 2L. And then what is frequency 3 in terms of the first harmonic? It should be 3 times the first harmonic. So then what is the pattern? What's the general formula if for the wavelength in a standing wave, it's fixed at both ends in terms of length and the number of antinodes n? Okay, what is the pattern? So see if you guys can figure that one out. We look at ours from before. For the first one, it was lambda equals 2L, lambda equaled L, and then lambda equaled 2/3 L. N was 1, so that was 1 first harmonic, 1 antinode. Second harmonic, 2 antinodes. Third harmonic, 3 antinodes. So lambda is 2L over N, 4L over 2N. Oops, what was that? That went away. And so that's kind of the general equation for my wavelength. So my wavelength is going to be 2L divided by the number of antinodes. Does that make sense? So if we look at this one, we've got 2 times the wavelength divided by the number of antinodes divided by 3. So see if that makes sense. A couple notes for the rest of the worksheet. So now take a look at part 2. Part 2 is a string that's fixed at one end and open at the other end. So on the right side of your paper, which I guess is this side. The right side of your paper, you see a node already placed in there. So you need a node on the fixed end, and then it would be an antinode on the other end. And that's a little bit more complicated. So see if you can work through that one. And then look at part 3. Okay, part 3 is a string that's open at both ends. If you look on your paper for part 3, there's nodes all the way down the right side. Those shouldn't be there. That was a printing error. So the nodes on part 3 should not be there, because if it's a string that's open at both ends, it's able to oscillate at both ends, then those are both going to be antinodes. So for your first harmonic, you're going to have a node in the very middle. There are some websites online where you can kind of check your answers to these if you're really struggling, or else we're going to go over them Monday. So have a fabulous day. Bye.